So this week we will continue our discussion on learning graphical models. Last week we studied the problem of parameter learning. In parameter learning, we assume that the structure of the graphical model is given to us. We know whether the underlying graphical model is a directed graph or undirected graph, and we know a lot about we know the entire structure completely. Then we make observations. So we draw samples from this graphical model by observing values the different vertices can take and use this to identify the parameters of the probability distribution that factorize over the graphical model. So we studied the fully observed case first when all the parameters were known. Then we considered the case of partially observed model where only a subset of the variables were known. And in that case, we studied the expectation maximization algorithm in general and the detailed exact case of hidden Markov models for parameter learning. Today, we will take the next step and discuss what can be done in the case of structured learning. So in this case, we do not know the structure of the graph and we do not know the underlying probability distribution either. We are just given some samples and we want to find the best structure of the graphical model that fits to these samples. This is obviously a much more challenging problem, so we will make several simplifying assumptions. So at first, we will assume that the distribution that we want to approximate is actually given to us. So we'll assume that Q of x1 to xd is a d-dimensional distribution that is already given to us. And we want to approximate Q with a simpler distribution, Px. Now, what do we mean by a simpler distribution Px? We will require that Px actually factorize over a simple graphical model. And the graphical model that we will consider in this case will be a tree. So here is an example. Qx as such consists of three variables x1, x2, x3. And so d is 3 in this example. So the original QX has no structure, so the underlying graph will be a fully connected graph, and so there is no particular way to simplify this. However, what we want is that the underlying the px that we are going to approximate Q with should factorize on a tree. Now we will not fix which tree up front. We will not decide whether it's tree tau 1 where x1, x2 and x3 are connected in this form or tau 2 or tau 3. So what this tree imposes is that there is some conditional independence between x1, x2 and x3. In the first case, x1 and x3 are independent given x2. In the second case, x2 and x3 are independent given x1 and so on. However, we do not know upfront which of these trees has to be selected. That will be coming from the data. All we know is that there should be some sort of conditional independence that should be imposed in this way when we try to approximate Q with respect to P. So we have a twofold question. One is which is the best tree to select to approximate the original distribution. And then the second question is what are the parameters of the distribution once the tree is selected. So from now on, we will let FD be the set of all distributions that factorize on some tree over D variable nodes. So we will not fix the tree. We will consider any kind of a tree consisting of the D variable nodes. So in this example, D is 3, so we have 3 possible trees. And we will assume FD to be the set of all possible probability distributions that factorize on any such tree. What we want to do is we want to solve this problem. We want to find the distribution that is closest to Q in the sense of the Kullback-Leibler divergence that we have discussed before. And P, the constraint is that it should be factorizing with respect to some tree consisting of the D variable nodes. In other words, it should be in the set FD. Now, this is not a straightforward minimization that can be done, because if we just do an exhaustive search over all possible trees, there will be a very large number of trees. There will be approximately D to the D trees. Even if we consider the case of line networks, where the graph is just a straight line, there are d factorial ways of ordering the nodes. So there are already d factorial combinations just for line networks. And trees will be much more. So you have about d to the d trees. And so you have super exponentially many trees to search for in terms of d. And so this search is not practical. The good news is that there is an efficient polynomial time algorithm to find the optimal tree structure uh, that is part of this minimization, as well as the resulting distribution p hat of x. So if we restrict to ourselves to those distributions that factorize over trees, this minimization in fact can be done efficiently in polynomial time. Of course, we cannot do a brute force search, but we will propose an algorithm that will do it efficiently. For that, we do the following. We will do it in two stages. We will first identify the right tree structure associated with the given distribution, and then we will show how to compute the probability that factorizes over this tree structure that ultimately solves this problem. So this is done by as follows. We let tau d denote the set of all undirected trees with d nodes, and let tau p hat be the tree associated with the optimal distribution p hat. Then tau p hat can be obtained by solving the following max problem. We maximize we consider the pairwise mutual information between all variable nodes that have an edge in the given tree. So xi and xj, or actually I should have ij here, not xi, xj. So we take the sum over all ij in the tree tau. We look at the mutual information between the associated variables xi and xj using the q distribution. So we marginalize q with respect to xi and xj to compute this mutual information. We sum over all edges, and then we pick a tree for which this quantity is the largest. So here note that IQ of xi xj is the mutual information between the variables xi xj with respect to the q distribution. So in our 3-node example, we had 3 trees, tau 1, tau 2, tau 3, as you saw here. And in each case, you can compute the mutual information. For tau 1, we have I of x1, x2 plus I of x2, x3. For tau 2, we have I of x1, x2 plus I of x1, x3. And for tau 3, we have I of x1, x3 plus I of x2, x3. If this quantity is the largest, then we will pick tau 1 as our tree structure in this optimization. The second quantity is largest, we will pick tau 2 as our optimal solution here, and so on. Now again, at the first glance, it seems we have to compute the objective for each tree and then find the best one. And this is again not practical because the number of trees will quickly grow with D. However, there is going to be an efficient way of doing this, and that is given by a method called the Chow-Liu algorithm. So what we will do next is first sort of discuss the practical aspects of this problem. We will explain how to apply this algorithm when we do not know Q, but we only have access to observed samples. So imagine we do not even know Q, but we just have access to n samples, each being a d-dimensional vector of the d features that we have. And using this, we want to find the best possible tree structure and the associated distribution that factorizes on it. Secondly, we will explain how this maximization can be done efficiently without a brute force search. And finally, we will provide a proof of this, why this actually works, why this objective function will allow us to find the tree that is best for the particular Q as we defined. Okay, so what if we don't have access to Q of x1 to xd, but all we have access to are just n samples, x1 to xn, each of them having d features. Now computing q hat of x, in this case using the empirical distribution, is not going to be practical, and this is because if we just try to use the empirical estimates, we will be stuck with the curse of dimensionality. And we discussed this before a few weeks ago. So even if all the xi's are binary valued and d is 20, there are 2 to the 20 possible vectors for which we have to assign the probability distribution. If we have like say 50 or 100 samples, we just won't be in a position to assign values to all these parameters, and so computing q hat of x is just not going to be feasible. However, the good news is in the Chow-Liu algorithm, we do not need to compute q hat of x for the whole. That was the whole point of graphical models. We do not want to compute empirical estimates for the whole data vector. The Chow-Liu algorithm only requires us to compute pairwise estimates for the distribution. So for any xi and xj, for any two I variables xi and xj, we just can easily compute the empirical estimate for this joint distribution. All we have to do is sum over all the n examples and do a frequency count of how many times this particular symbols xi and xj jointly occur in our samples. And this, so for example, if xi is 0 and xj is 0, we just, for the I and jth position, we just see how many times we saw the 0, 0 pair in the I and jth position, and that fraction will be assigned to q hat of 0, 0 for this choice of I and j, and so on. This is just a simple empirical count that can be easily done. Once we have that, we use the formula for mutual information to compute this, and we do this for all variables xi and xj. In other words, we fill a matrix like this. In this matrix, the rows and columns are all like the variables we have. So this is x1, x2 up to xd, x1, x2 up to xd. The diagonals are not going to be relevant because we only consider the case when the variables are independent. We only have to look at upper diagonal values. So because the matrix is symmetric, so first we'll compute I hat of x1, x2, then I of x1, x3 up to I of x1, xd, then I of x2, x3 up to I of x2, xd, and so on. So these are the quantities that need to be computed. Once we have computed these, we can in fact use this matrix to solve the optimization problem that we are interested in. And this is in fact, solving this optimization is a well-known problem in the CS literature. It is known as the minimum spanning tree algorithm, MST. We may have seen it in an algorithms course, but the point here basically is that a simple greedy algorithm will be able to solve this. So the steps are outlined here in the notes. We first calculate the matrix of mutual information as shown on the previous page. Then we initialize the tree with respect to a single node. So we can pick any arbitrary node. Then at each step we grow the tree by one edge, and this is done as follows. Among all vertices not yet included in the tree, we consider that vertex whose inclusion leads to an edge with the largest possible mutual information. And we keep repeating this until we terminate. So here is an example. X1 is say the first node selected in the tree, and we have three other nodes, x2, x3, and x4. Now we want to add one particular node into the tree. Should we add x2, should we add x3, or should we add x4? To do that, we look at the pairwise mutual information in the first row. So we look at I of x1, x2, I of x1, x3, I of x1, x4. And let's say that I of x1, x3 is the largest. Then what we do is we put in x1 and x3. Now we have to decide whether to pick x2 or x4 and put it in the tree. Now again we ask the question, if I were to put x2, what is the largest amount of mutual information I can add versus if I were to put x4. So in other words, we pick an edge here which will have the largest mutual information, between the selected node and one of the nodes in the tree. And let's say I of x1, x4 has the largest mutual information. Then x4 gets added to the tree. So now I have x1, x3, and x4. So my tree looks like this. And then I have to add x2. So x2 gets connected to the node in the tree with which leads to the largest mutual information. So let's say I of x2, x4 had the largest mutual information. So this is basically the idea, and this algorithm will terminate in in basically the number of step in will when all the vertices have been visited, and each time we have to add a node with the largest mutual information. So this is a greedy algorithm. You can look up on minimum spanning tree in the literature. It's a very sort of popular algorithm. I have not rigorously described it, but this is what you will do, and keep repeating until all the vertices have been completed. Here is the proof of the Chow-Liu algorithm. Uh, in this proof, we will first fix a G. We'll assume G is an undirected tree with B is the vertices, E is the edges, and we consider a joint distribution that factorizes over G. So we have a distribution over x1 to xd that factorizes with respect to G, and this distribution can be expressed in the right hand side. So we can take the product over all marginal distributions for all the variable nodes p of xi, and we also take the pairwise distribution between each pair of nodes on the edges and divide them by p of xj and p of xk, the pairwise marginals, or just the respective marginals, p of xj and p of xk. So if you have a distribution that factorizes on a tree, it can be expressed in this particular form. Now, this is not quite the form we discussed when we were discussing undirected graphical models. At that time, we said that the joint distribution factorizes into a product of factors, one corresponding to each clique in the graph, or in the case of a tree, each edge in the tree. And then there was a normalizing constant z. Turns out that if you do have a tree, then that normalizing constant can be worked out explicitly. That's a simple exercise, so I'm not going to do it. And it can be shown that in this special case, the joint distribution factorizes in this particular form. So what we will do is we'll let Pg be the set of all distributions that factorize with respect to G. And for now, we will fix G and solve this problem. We want to find the distribution that factorizes with respect to G and that is closest with respect to Q. That will give us an objective. That will tell us how much the cost is for this particular G, and then we will pick one, the G that will give us the smallest cost. So we'll do it in two steps. Assuming G is fixed, we'll find a P that minimizes this quantity. Then we'll solve that explicitly, and then we'll select the G with the smallest cost. So let's Pg be now the set of distributions that factorize with respect to G. So we want to find this quantity now, and let's call it P hat of G. And then this quantity, the relative entropy or the Kullback-Leibler divergence, can be written in this form. This is the same expression. We break the log, we get summation over x qx log qx minus summation over x qx log px. The first term does not depend on p, so it's a constant. So we can, instead of doing the minimization, we can do this maximization, arg max p in pg qx log px. Now Px has this form. It is the product over all x p of xi where I is in V, and the product over jk in E, p of xj xk over p of xk times p of xj. So the log times the product simplifies nicely. You can write it as a summation over I in V log of p of xi plus the summation of jk in E log of p of xj xk divided by p of xj p of xk. And then we have the outer summation over qx. So this can be written as, if we interchange the first two summations, then we have summation of I in V and summation over x qx log p of xi. But because this term does not include the other symbols in x except xi, we can marginalize qx with respect to all other variables, and what we are left with is q of xi here. So the first term is now summation of I in V, summation in xi, q of xi log p of xi. And the second term, similarly, if you interchange the order of summation, is that you get summation over jk in E, summation over xj xk, q of xj, q of xk log p of xj xk divided by p of xj, p of xk. So we want to maximize this. The good news is that this maximization can be done explicitly, and all that we have to do is that the p that is optimal here will be one that basically matches q. So p of xj p of xi xj should equal q of xi xj for all ij in E, and p of xi likewise will equal q of xi once you marginalize. So if we plug this in, the objective is now summation on I in V, summation over xi, q of xi log q of xi, plus summation of ij in E, summation over xi xj, q of xi xj log q of xi xj divided by q of xi q of xj. The second term is the mutual information between xi and xj, and the first term is the entropy, minus of the entropy. So now your objective becomes summation of I in V minus each q of xi plus summation of ij in E, iq of xi xj. And we want to now, so for given g, this is the quantity that we get. And now, because we flip the